During a total solar eclipse, the sun becomes a black coin and a pale crown appears. The corona, a halo of streamers and loops reaching far into space. It looks like it ought to be cold. Step away from a fire and the air cools. So why is the gas above the sun's surface not cooler, but around 1,000,000 degrees, hundreds of times hotter than the visible surface, whose temperature is read off its spectrum at about 6,000 degrees? That question began as a mistake. In the 1800s, eclipses were the only chance to see the corona at all, so astronomers brought spectroscopes and split its faint light into a fingerprint. In 1869, a bright green emission line appeared that matched no known element. The sun seemed to be advertising a new substance. It got a name, coronium. The idea lasted because the corona is hard to study. The photosphere is blindingly bright. The corona is faint. Totality is short. Then, atomic physics caught up. Quantum mechanics revealed that some spectral lines are forbidden, rare transitions that only show up in extremely low-density gas, where collisions don't interrupt them. The coronal lines were mostly forbidden lines. In 1941, Bengt Edlund connected the mystery lines to ordinary elements in extraordinary states. Iron atoms stripped of many electrons. The green line could come from iron missing 13 electrons. That missing electron count is inferred from the exact wavelengths of the lines, and it acts like a thermometer. Only a brutally hot plasma keeps bumping electrons off that efficiently. The corona had to be around 1,000,000 degrees. That solved coronium and created the real paradox. How can the sun's atmosphere get hotter as the distance from the surface increases? 1,000,000-degree corona has another consequence that can't be ignored. Hot gas has pressure, and pressure pushes outward. In 1958, Eugene Parker argued that a corona that hot cannot sit still. It must expand into space as a continual wind. It sounded outrageous, until spacecraft carried particle detectors beyond Earth's atmosphere and measured it. A steady stream of charged particles, hundreds of kilometers per second, washing through the solar system. Even comet tails had been pointing the same way all along. The solar wind is the corona, escaping, so the coronal heating problem is not cosmetic. It sets the conditions of space weather, auroras, radiation storms, and the environment every spacecraft lives inside. 1,000,000 degrees should melt anything. Why doesn't a spacecraft fry? Because there's almost nothing there. Compare densities. A cubic centimeter of air at sea level holds about 25 quintillion molecules, 25 followed by 18 zeros. A cubic centimeter near the base of the corona holds roughly 1 billion particles, 1 followed by 9 zeros, inferred from the brightness of coronal ultraviolet and X-ray emission, and from how easily collisions would quench those forbidden lines. Divide. 25 quintillion divided by 1 billion is 25 billion, so the corona has about 25 billion times fewer particles. Each particle is much hotter, but there are so few that the total heat content in a volume is tiny. 2,000,000 degrees compared to 300 is about 7,000 times more energy per particle. 25 billion divided by 7,000 is a few million. So per unit volume, the corona can have millions of times less thermal energy than room air. Ultra hot, ultra thin. That pushes the mystery back where it belongs. What keeps the corona hot in the first place? Sunlight isn't the heater. The corona is too transparent. Most light just passes through. Conduction isn't the answer either. It would rather erase temperature differences. The energy must rise in a different form and only later turn into heat. The sun's surface is a boiling conductor of plasma, threaded by magnetic fields. Surface motions drag the magnetic field around like fingers twisting rubber bands. That twists and braids the field above, storing energy as magnetic stress. Release that stress, and the plasma heats. At first, many researchers hoped sound waves could do the job. Convection launches pressure waves. Those waves could steepen into shocks and dump heat. The trouble is that the heating pattern follows magnetic structure far better than it follows the sun's loudness, and acoustic energy tends to dissipate too low in the chromosphere before it can maintain million-degree gas higher up. Magnetism stayed in the spotlight, and two main routes emerged. One route is wave heating. In a magnetized plasma, the field's tension supports alpha-Venn waves, ripples that travel along field lines, carrying energy upward. The open question is dissipation, how those relatively organized motions get shredded by turbulence and finally absorbed at very small scales as heat. The other route is reconnection. Stressed magnetic fields can abruptly rearrange, snapping into a lower energy geometry and converting magnetic energy into particle energy and heat. Solar flares are the loud version. The quiet version may be countless tiny reconnection events, often called nanoflares, adding up to steady heating. These routes overlap. Waves can trigger reconnection. Reconnection can launch waves. The detective work is sorting out where each dominates. Wave heating should leave the corona full of oscillations and non-thermal motions, and it should imprint specific kinds of magnetic fluctuations in the young solar wind. Space telescopes routinely see loop motions, and Parker's solar probe has measured strong Alfvén-like fluctuations in regions where the solar wind is still being accelerated. Nanoflare heating predicts a different fingerprint, a blizzard of tiny brightenings with a characteristic distribution, plus brief pockets of very hot plasma that appear and cool rapidly. That's hard to confirm because the corona is transparent and the faintest events skirt the edge of instrument sensitivity. But the evidence for bursty heating keeps growing. The sun radiates about 60 million watts per square meter from its surface, a number computed by taking the sun's total luminosity, measured from the sunlight arriving at Earth, and dividing by the sun's surface area. Coronal heating needs something like a few hundred to a few thousand watts per square meter. 60 million divided by 1,000 is 60,000, so the corona only needs roughly 1 part in 60,000 of the energy flowing through the surface layers to be redirected upward and dissipated. The same physics connects wildly different places. Magnetic reconnection powers auroras and disrupts laboratory fusion plasmas. Alfvén waves and turbulence show up in planetary magnetospheres and in astrophysical disks and jets. Other stars have coronae too, and the most active ones bathe nearby exoplanets in flares and particle storms. As of 2026, 0104, there still isn't a single agreed recipe for coronal heating. Different regions may use different mixes of waves, turbulence, and reconnection, and the mix may change with the solar cycle. A major bottleneck is direct measurement of the coronal magnetic field, the reservoir of energy, using subtle polarization signatures in faint light. New observations from DKS, Solar Orbiter, radio arrays, and Parker Solar Probe are starting to track energy from surface motion to magnetic stress to heat to solar wind in the same events. The paradox that began with a green spectral line has turned into a lesson about nature's consistency. The same electromagnetism that makes a compass needle turn can, in a plasma star, build a 1,000,000-degree atmosphere above a 6,000-degree surface. The lingering question is pointed. If magnetic fields can rearrange a star's outer layers so dramatically, what does that imply for the climates and the chances of worlds orbiting more violent stars? Like, if this was interesting, hit the subscribe for more and turn that notification bell on.